welcome to the practicals of biochemistry. So today we want to discuss about the enzymatic hydrolysis of starch. So normally in the physiology you already studied. So, as a part of physiology in the digestion, we studied about the digestion of the carbohydrates. So very simple step in the physiology of carbohydrate digestion is the, so what happens, we are taking the carbohydrate diet. Carbohydrate diet majorly contains the starch as a major carbohydrate consistent. So the starch in the presence of salivary amylase. So our saliva contains the enzyme that we call as salivary amylase that acts on the starch that causes the breakdown of the glycosidic linkages and will ultimately convert that into the monosaccharide glucose. Okay. So now we are determining the activity of the enzyme. So how the enzyme is converting starch into glucose. And one very important thing, we need to determine whether it was converted the starch into glucose or not. So that we are determining with the help of the reagent DNAC, dinitrosilicic acid reagent. So already, so you done the experiment estimation of the reduced sugars by DNAC method. So there we are reacting the DNAC reagent with the reduced sugar. So automatically that will react with the reduced sugar and itself will reduce it to 3-amino-5-nitrosalicylic acid. So automatically it produces in the orange red color. The same principle we are applying in this experiment also, and we are determining the enzymatic hydrolysis of the starch. Okay. So first, what are the requirements that we call as what are the chemical requirements to do the experiment? The first one is the saliva. So the saliva will make in two ways. One, we will collect 1 ml saliva, we will dilute that to 10 ml with the distilled water. One is in dilution. So the other one is we will take 1 gram of the alpha amylase. So enzyme powder will be there. We will dissolve in 100 ml of water. So that we call it the 1% enzyme solution. See, in any way we can we can prepare the enzyme solution. So the second step is we have to prepare the starch solution. So for the preparation of starch, first we have to make the pH 6.8 buffer. So we need to provide the favorable conditions in order to get the maximum activity from the enzyme. So for that, so the starch is the substrate. This is substrate starch we are dissolving in a pH. So 6.8 automatically that will produce the favorable condition for the enzyme, and the enzyme immediately act on the starch and converts the starch into glucose. So this is the these are the requirements. Apart from this, we need DNAC reagent. So DNAC reagent is the very important one. DNAC reagent. So DNAC reagent is the very important one. So that we need DNAC. So DNAC reagent. So DNAC reagent is a very important one. So that estimating the reducing sugars. Okay. So these are the requirements, and these also we are estimating with the help of the colorimeter. So at 540 nanometers. So the next part in the experiment is the principle. So generally this principle will be in two steps. Step one, so is the substrate in the presence of enzyme is converts into glucose. So here we are taking the substrate starch. We can take glycogen also, but starch is a very easy one because of that reason. We are taking the starch. So this salivary amylase acts on the starch, convert the starch into monosaccharide glucose. So glucose is the one important example of the reduced sugar. Okay. Next, in the second step, the reduced sugar glucose. This is the structure of the glucose. So this glucose it reacts with the dinitrosilicic acid reagent, and it forms the gluconic acid. Simultaneously, this DNAC 3,5 dinitrosilicic acid is reduced to 3-amino-5-nitrosalicylic acid. So this is the structure of 3-amino-5-nitrosalicylic acid. So here initially it contains 2 nitro groups because of that reduction. So this nitro group will become amino. So because of that reason only this orange yellow color is becoming orange red color. The intensity of the orange red we are we are estimating, and based on that we are determining the enzymatic hydrolysis of the starch. Next, we will go to the procedure of the experiment. So how we are determining the enzymatic hydrolysis of the starch. So as we know, as we discussed, we need the substrate, that is the starch solution. So 1% starch solution, very simple. We take 1 gram of the starch, we'll dissolve that in 100 ml of the pH 6.8 copper. So automatically we'll get the 1% starch solution. Second, enzyme solution, we are taking 1 ml of the saliva, we are diluting it to 10 ml with the distilled water. So 1:10 dilution. Or we can take the 1 gram of the salivary amylase, alpha amylase, and we'll dissolve in 100 ml of water. In that way also we'll get the enzyme solution. Third one is the DNA seriation. So now see the process. So the very important step is the take 10 test tubes and label them as 1, 2, 3, 4, 5, 6, 7, 8, 9, and as a blank. So okay, total take 10 test tubes, label them as a 1 as a blank, remaining as 1 to 9. Or we can label in another way also. We can label as a 0, 15, 30, 45, 60, 75, 90, 105, 120, and blank. So anyone is okay. So that, and here what we are doing with respect to time, the hydrolysis will vary. If the enzyme has a more time, automatically it will act on the substrate for a long time, and it will convert the maximum substrate into a product. So for example, if less time is available, what will happen? So very little amount of substrate will convert into product. Almost the maximum amount of substrate will be as such. So here also we are determining, we are going with the same procedure and principle, and we are determining the enzymatic hydrolysis of the starch. So after labeling, the first test tube preparation. So take 1 ml of starch, then add 1 ml of the enzyme solution immediately. So here I mentioned the column time. So this time indicates that how much time we have to wait to add the DNA reagent. So in the case of that test tube 1 or the test tube which was labeled as 0, so in the test tube we have to take 1 ml of starch solution, 1 ml of enzyme solution. Immediately we have to add the DNA. So here we are not giving any time for the enzyme to do the catalytic activity. So because of that reason we label that as 0. Then add 1 ml of the DNA reagent. So DNA reagent actually will stop the catalytic activity and will quantify the amount of reduced sugar present in the sample. In the same way, remaining tubes also. So in the tube labeled as a 15, so there 1 ml of starch solution and 1 ml of the enzyme solution, and wait exactly 15 seconds, and then add 1 ml of the DNA reagent. Next, third tube, 1 ml of starch solution, 1 ml of enzyme solution, and wait exactly 30 seconds. After 30 seconds, add 1 ml of the DNA reagent. Next, fourth test tube. So 1 ml of starch solution, 1 ml of enzyme solution, 45 after 45 seconds, add the DNA reagent. That way, in a series, you add after 60 seconds, 75 seconds, 90, 105, 120 seconds. In the case of the test tube which was labeled as 9 or 120, so then what we will do after adding enzyme solution to the starch, exactly we will wait 120 seconds, then we will stop the catalytic activity by adding 1 ml of the DNA reagent. So after, in that way we will make the test tubes 1 to 9. In the case of blank, so we will take 1 ml of the starch solution, we won't add enzyme solution. So we won't add enzyme solution, we will add 1 ml of the distilled water. So in order to make uniform quantity, uniform volume. So then immediately we'll add the DNA and we'll make it that as a 0. So in order to measure the OD values of this 1 to 9 test tubes. So this is about the procedure. So after adding DNA, incubate at room temperature for 5 minutes and boil on the water bath for 2 to 3 minutes. Then measure the absorbency of the tubes against the blank. So at 540 nanometers. So very simple experiment. So first label the test tubes, then so add 1 ml of our solution into all the test tubes from test tube 1 to blank. So then depend on then add the enzyme solution one by one So depend on the time, add the DNS solution. So that we call as the time lag. So if the test tube labeled as 45 means 45 seconds you have to wait. Then you have to add the DNS reagent to stop the reaction to quantify the reduced sugar present in the sample. So in this way, we'll do the.
Okay.
So label the test tubes as 1 to 9 and one more as the blank. So in this way, you label the test tubes. Now, into all the test tubes, take 1 ml of the starch solution. Okay. So now I am adding the saliva. So into each test tube with respect to time. So now into the test tube 1, I am adding 1 ml of saliva. So as this is there was no time gap, so immediately add. Immediately add 1 ml of the TNSA reagent. So into the second test tube, now add enzyme solution. Exactly wait 15 seconds. Okay, after 15 seconds, add DNSA. So now into the third test tube, add 1 ml of saliva. So wait 30 seconds. So now the fourth one. So again add 1 ml of saliva. Wait 45 seconds. After 45 seconds, add DNSA. Next one, fifth tube. Here also add 1 ml of saliva. Adding saliva. Wait 60 seconds, then add 1 ml of DNSA reagent. Now add, after 60 seconds, add 1 ml of DNSA reagent. Add 1 ml of saliva. Wait 75 seconds. So into the 6 tube, after 75 seconds, add 1 ml of DNS. Now add 1 ml of enzyme solution to the test tube. Test tube 7. So now regarding the blank preparation, so take 1 ml of starch solution. So regarding blank preparation, so take 1 ml of starch solution, 1 ml of distilled water, immediately add 1 ml of DNS reagent. So in this way you make the blank. So now after preparing all the mixtures, so keep all the test tubes in the water bath for 5 minutes. So automatically the DNSA will react with the reduced sugar, that is glucose, and will form the orange red color. Next, that intensity of the orange red color we will measure by using colorimeter at 540 nanometers. So uniformly boil all the mixtures in the water bath for 5 minutes. So after 5 minutes boiling, so take the test tubes, bring out the test tubes from the water bath, cool the mixtures. So after boiling, so cool the mixtures and measure the absorbences by using calorimeter at 540 nanometers. First, so auto zero the instrument with the blank. So this is a blank solution. So by using this blank, auto zero the instrument at 540 nanometers. So first set the wavelength to 540 nanometers. Then keep the blank and adjust the reading to 0. Okay, so now the instrument was auto zeroed with the blank. Take out the blank. So now one by one to measure the absorbances. So first I am taking the 0 test tube. So means 0 seconds. So the absorbance is 0.29. So next, let's take the second test tube. So the body value is 0.36. Take the third tube. That is 0.37. Next, measure the absorbance of fourth tube. That is 45 seconds. So measure the absorbance of the fourth tube. So mother, take the fourth tube sample into the resistance. So measure. So that is 0.38. So very slow reading we are observing here. So that is because of the proper reaction. So next, fifth tube. So the absorbance is 0.46. The sixth tube. Zero 0.53. So next, take the seventh tube. 0.57. Please we measure the remaining two also, 8 and 9. 0.59. So last tube, 9. 0.59. So now, with the help of those OD values, draw the graph. So now, draw the graph. So on x-axis take the time, y-axis take the OD value. The scale on x-axis is 1 centimeter is equal to 15 seconds. So based on my OD values, I am taking as the on y-axis the scale is 1 centimeter is equal to 0.1 unit. In that way, draw the x and y-axis. Now intersect the points. So the first one at 0 seconds. So the value is 0.29. So Okay, at the 0, so we got value 0.19. So you draw that one on the graph. Then 15, so that is 0.36, somewhere around here. 30, 0.37. At 45 is 0.38. At 60, it is 0.46. At 75, it is 0.53. At 90, it is 0.57. At 105, it is 0.59. At 120 also it is 0.59. So in that way you touch all the points, you draw a curve. So in this way we can assess that the enzymatic hydrolysis is done, the starch is converting into glucose. So because of that reason only, as the time increases, we get the more absorbance values. Okay. So in that way we'll determine and we'll report. Okay. That is about the experiment enzymatic hydrolysis of the starch.